And so today I'd really like to talk to you about momentum and impulse and collision review. Those three are all part. So a review essentially on momentum, impulse, and collision. So let me write that up here. Momentum, impulse, and collisions. Momentum, impulse, and collisions. We'll start with momentum. We hear things on the radio and on sports shows such as ESPN. We hear things on the radio such as Fox Sports. They will all say that player has got momentum. Those teams are really gaining up the momentum. Momentum is quite literally, we can define it as mass in motion. Mass in motion is what momentum is. So, from this statement here, mass in motion, we can basically derive the momentum formula. We know that mass is going to be m. We know that motion is going to be velocity. We're going to describe motion here as velocity. And momentum, we don't use an m because remember we're using an m here already. So we're going to use p for momentum. And thus we get the momentum equation. P is equal to mv. So momentum is equal to mass times velocity. And you can turn these equations into, what you can do that now is you can turn that into m is equal to p over v. And from there you can say that v is equal to p over m. So this lets you solve for pretty much anything with having to do with finding the number of either momentum, mass, and velocity, given that you are given that you have the values of either m or v or p. So if you have two of these values, either p or v, p or m or v, then you can solve pretty much for the third variable that you don't have. Now let's take a look at some example problems with momentum. So if I were to say that I have a 15 kilogram linebacker running at, let's say 10 meters per second, and we're trying to find momentum. Now we're going to multiply 15 kilograms times 10 meters per second, and that's going to give us 150. But not only 150 kilograms, but 150 kilograms times meter per second. This is giving us the units for momentum too, which is kilogram meter per second. If we were given this number here, let's say we were given 150 kilograms times meter per second and running at 10 meters per second, we can find the mass of the object. So if we do m is equal to p over v, then we can say that m is equal to 150 kilograms meter per second over 10 meters per second. And that's going to give us the mass, which is going to be 15 kilograms, because meters per second here will cancel out, giving us 15 kilograms. That's the momentum there. If we were to take a look at now changes in momentum, that would be what we call impulse. Impulse is the change in momentum. So if I thought that change in momentum. The change in momentum. So we know that from the previous unit, force is equal to mass times acceleration. F is equal to ma. We also know that acceleration is equal to F net divided by m. So if we take a look, we can find the impulse equation by essentially substituting acceleration F net over m into this formula. Now we also know that that acceleration is also equal to the change in velocity over the change in time. So doing that substitution here, we can say that force is equal to mass times the change in velocity over the change in time. So if we multiply both sides by the change in time, then we get force times delta t is equal to m times delta v. And if mv is equal to momentum, then we know that m delta v must be momentum, or must be the change in momentum. So if we have force times delta t, we know that this equation that we have here is going to be the change in momentum. So we can use this formula if we are given the change in momentum, or even the force for that matter. We can find out what the missing variable. So if I were told that that an object started at some momentum and ended up with a change in negative 270 kilograms meter per second. So that's the change in momentum. So we've changed 270 kilograms meters per second. We've lost that much momentum. So now, and we say that lasted for, let's say, we'll say 9 seconds. So that was a pretty long change in momentum. So now we need to calculate the force. So we do force is equal to m delta v over delta t. We know that m delta v is equal to negative 270 kilograms meter per second, because we're already given m delta v when we given this, because this is the change in momentum, and this is the change in momentum. So now if we divide that by 9 seconds, we're going to get the units of force, which are essentially newtons, and we're going to be getting 270 over 9, which is going to be 30 newtons. Now, is it positive or negative? Well, let's find that out. Let's say that the original momentum is going to be going this way. So if the original momentum is going this way towards the right, then we are going to need to have a force, and it's a losing momentum, then we need to have a force going to the left, because that's how we're going to lose. We need to have a force that's opposing the direction of motion. That way we get a negative change in momentum, because we're not losing mass, but we're losing velocity. So we need, in order to lose that velocity, we're going to need a force that opposes that. So the force, drawn green, goes this way. So the purple here is the momentum, the green is the force, and the result is going to be a force in the negative direction. So really we should put a negative 30 newtons here, because the force is going to be going the opposite direction. The last concept here in this quick review is going to be collisions. We have two types of collisions, so I'm actually going to draw a partition down the center. On one side I'm gonna draw, or I'm gonna just place here, I'm going to put elastic collisions. Elastic. Elastic collisions. And on this side I'm going to put inelastic. Inelastic collisions. Those are the two types that we're going to be dealing with here. So inelastic collisions, let's start actually with inelastic, because that's actually the easier one. In an inelastic collision, I'm just going to draw a quick diagram. Oops. Let's try that again. In an inelastic collision, essentially what's happening is the two objects are colliding and then sticking together after the collision. So imagine if we had, here's the floor, and we had a ball here and it's moving this way, and we had another ball right here, and that ball is just stationary. After the collision, in an inelastic collision, the two balls would now be moving as if they were stuck together. This is exactly what happens during a game of billiards or pool. What happens is that you shoot the cue ball at your target, and when the cue ball hits the target, it basically, both of them go together. So as you can see here, if this is M1 and this is M2, the mass of this object here is going to be M1 plus M2, because now they're moving as one whole body. So if we draw the equation for this, we can see here that we're going to see that the momentum, due to the principle that's the conservation of momentum, so that's very important here. We know that the momentum is always conserved. So in collisions, so we know that the momentum 1, the value of momentum 1 is going to be equal to the momentum 2. So before and after, they're going to be the same momentum. Now we also know, which will be useful for equations later, that the change in momentum of mass 1 is going to be equal to the change in and opposite to the change in momentum of the other one. So in other words, if mass 1 changes by 3 kilogram meters per second, mass 2 is going to change by negative 3 kilograms meters per second, in accordance with this principle here. So these two actually deserve to be paired up here. That'll come very handy when you're solving for total momentum. So in other words, if the momentum is going to be equal, that means the mass of 1 times the velocity of 1, of mass of 1, plus the mass of 2 times the velocity of 2. Because remember, this is the total momentum in our system. Even though this one here in our example is not moving, it still has a momentum of 0. So the mass of 1 times the velocity, that's the momentum, plus the momentum of object 2 has to be equal to the momentum after the collision. Now, here's the thing. The masses are going to be equal. So we're going to have to add mass 1 and mass 2. And then they're both going to be moving together at the same velocity. So in that sense, we get this equation: mass 1 velocity 1 plus mass 2 velocity 2 is going to be equal to mass 1 plus mass 2 times the final velocity. Next we have elastic collisions. Elastic collisions are a little bit different and slightly harder, however, not by much. In an elastic collision, the two objects basically springboard off of each other. So if we have, this time I'm going to actually draw to both of the objects in motion, because it just makes it easier to conceptualize. In an elastic collision, what happens is the two objects don't stick together. So this is before the collision, this is during the collision, and then after the collision it looks something like this, with both of them moving in opposite directions. So again, this is m1. So this is m1, m1, mass 1, mass 2, mass 2, and then mass 2. So these are all mass 1, these are all mass 2. So as you can see, the two objects are hitting each other, are moving towards each other, hitting each other, and then essentially going opposite. That's where this formula here is mainly going to come into play. So that means that in accordance to our conservation of momentum principle, what we say here is now again the momentum of the original momentum and the final momentum must be equal in the whole system. So is equal to. Now this is interesting because I'm gonna put a second subscript here. I'm gonna put I for initial, because remember the velocities might not be the same unless it's a perfectly elastic collision, in which case the velocities, they rebound with exactly the same velocity. But that's not the case in most instances. So I'm gonna put a second subscript. So this is mass 1 times v sub 1 sub I. Now the reason I did that is because after the collision we're still gonna have the same masses, but now these velocities might be a little bit different. They're gonna be v sub 1 or 2, and then sub f, because mass 1 might come into the collision with 10 meters per second of velocity, but then only leave with 5 meters per second of velocity. Now notice that this still is in accordance with our principle, and that's why this is very important here. In this case, if mass 1 comes in with x velocity and mass 2 comes in with y velocity, the velocities the masses, if they don't change, are going to the resultant momentum can be attributed to the change in velocity. So since in most collisions mass doesn't change, that's another reason why we put I and F, because the velocities will usually change because the masses are usually not lost. So just a quick recap of what we talked here. Momentum is basically mass in motion. It is described by the formula P is equal to m over mv, because momentum cannot be described by m because it's already taken by mass. Impulse is essentially the change in momentum. It is derived from this formula made by Sir Isaac Newton. F is equal to ma. It is the change in momentum is equal to F times delta t is equal to m times delta v. There are two types of collisions: elastic collisions and inelastic collisions. In inelastic collisions, the two masses will stick together, but in elastic collisions, the two masses will essentially rebound off of each other. This principle down here is called the conservation of momentum. Conservation of momentum. This principle, the conservation of momentum, is very useful when trying to figure out the final velocities of two objects, or however much the mass might have changed, or the total masses when the two objects collide if it's an inelastic collision. Thank you, everybody.